interesting. So here's what we're going to do. We're going to start with vectors. This is chapter 12, and we're going to talk about lines and planes. A lot of students have never seen a plane, never found the equation for a plane in 3D. It actually requires a careful understanding of vectors. That worries people, but I have a set process. Here's an example of two intersecting planes. Notice if two planes intersect, you get a line. Look around the room you're in. When two walls intersect, it forms a line. So we should be able to find the equation for that line, but how do you write the equation for a line in 3D? You don't have the concept of slope because three things are changing. What we do is we describe an object walking along it. This is just an example of the sorts of videos you're going to regularly see in my course. I've been making these for years. So that's just somebody walking along it. Now there's an infinite number of ways to walk along it, and so that leads to an infinite number of parameterizations, and students don't like that. The equation for a line is new. It's not bad, but we'll have to talk about it. So we'll talk about how to find lines and planes. When you're just talking about two curves, there's an infinite number of ways to parameterize each. So we'll have to talk about this issue of you could have one person walking on this curve, another person walking on this curve. That does not mean they run into each other. But that also, just because they don't run into it, doesn't mean the roads don't cross. And so that's one of the issues we'll have to talk about with parameterization is how can we tell if two things intersect? They have to be there at different times. If the two paths were ever at the same place, even at different times, then the paths cross. We'll have to talk about that. And that, I think I can give you the conceptual piece as good as anybody will do anywhere you go. So I will get you that piece. And I'll show you some cool visuals along the way. You don't really have to visualize to do this course. For my first 15 years, I didn't make these visuals. It was perfectly possible to do the course, but the visuals are fun. Then we'll talk about curves in 3D, and we'll talk about how we can't do the slope, but we can find vectors. Vectors that describe how we twist and turn and point the direction we go. If you've ever thought about 3D animation or describing the motion of something in 3D, those are important vectors. We'll talk about how to find them. Now, they're terrible to compute. It turns out that both the, whatever that is, orange and purple vectors are terrible to compute, and so we don't do very much of it in the homework. We do a little bit, but we can't do that much. We can find the red vector, no problem. So I have to talk about that, and unfortunately, the computations are bad. We won't do a whole bunch of those, but the ideas are important. Then we'll talk about what if we have something else moving around, like spiraling around in 3D. What are some measurement tools we can use to do that? And so we'll play this game, and then we'll say, well, what can we say about the speed or velocity? What can we say about the acceleration? Which way does the acceleration point? What do we even mean by acceleration? We'll talk about that. And I can't do that many practical examples. That's a sad thing about the course, but this is one example I'll do where I'm facing the y-axis and I throw a ball in the air, but there's a strong wind to the right. Where's it going to go? And based off of the forces, what can we say? This is not a physics course, but here's this object. We'll send it, and I use that to explain why these vectors are important. The vector that points the way it's going, the vector that points inward. Then all together, we can look at the path. And then we can study that path. And you can see where vectors become important in that study. So I find that quite interesting. So if you're going to study motion, you're going to have to know that. Okay, then we're going to switch in chapter 14. So chapter 12 was lines and planes and vectors. Chapter 13 was curves. Chapter 14, we're going to switch to surfaces. I call this a Pringles chip because it kind of looks like one. It's called a hyperbolic paraboloid. There's some interesting names we have to pick up along the way. They're not that bad. Students think they're bad, but I can explain how you can know the names. No big deal. But we're going to talk about studying that. And then we're going to do things like talk about the slope in one direction. This is a common theme in multivariable calculus, is to look at one direction at a time and figure out what the slope is and figure out how it changes. And then we'll talk about what happens if you step slightly to the right or left. What's the second derivative? And we'll use that to find places when the slope is zero in both directions. Here's another example. I'm going to draw what's called the tangent. Well, there's the tangent plane. We'll talk about that. But we'll find the slope in the x direction, which is this. And we'll find the slope in the y direction, which is that. They can be very different. And we'll talk about them. There's one place where both the slopes are zero. And I always say, when in doubt in calculus, take the derivative and set it equal to zero. We do the same thing here. It's just we have to take both derivatives and set both derivatives equal to zero. I can't quite hit it. Here we go. Boom. That's called a critical point. That will feel a lot like Calculus 1. In doing that, we'll be able to do some of the same applications you did in Calculus 1. For example, here's a plane. What's the biggest box you can fit under that plane? This is one of your homework questions that students really don't like. But visually, it's pretty stunning. So we'll find among all of these boxes, which box has the biggest volume. You'll do this when you get to section 4.7. That's pretty cool. Any sort of optimization question that has more than one variable can lead to this, and it'll feel very much like Math 124, sorry. So we'll do that problem, and I'll have visuals, put those on the discussion board. We'll talk about how do you find the actual maximum of a function above a region. If you're restricted to just above a region, that's confusing to students because we have to look at the sides and see that it's highest at one of the corners and lowest along one of the edges, and we'll study the edges one by one. This is one of the big differences about multivariable calculus is you're often working above a region. That's chapter 14. So you can see that the course is a bunch of short stories, really framing around 3D and the tools you need. Then we'll talk about volumes under surfaces, and we'll look at that in two ways. We'll basically use integrals in a clever way. So we'll look at slices. We'll have a region on the ground, and we'll have a surface. You can have the same region on the ground, but a different surface, and that's a different volume. And we'll play around with that. We'll say, well, what's the volume if we go this way? Well, the cross sections are triangles. What's the volume if we go this way? Well, the cross sections are rectangles. And so we'll have more than one way to set these things up. It's very valuable to learn how to describe a region. Okay, we then will finish with things where in chapter 15, where you actually have three ways of doing it. One way is like this. You could describe the cross sections that way, which looks like triangles. Another way is in terms of x. You can describe the cross sections that way, which looks like rectangles. And it'll always depend on the region on the ground and the surface. And then we'll have a third way, which is pretty cool and very valuable, which is what do we do if we rotate? That involves polar coordinates, and you really need those. In order to do polar coordinates, we'll have to talk in 2D a little bit and talk about how do we describe things in polar. And we'll talk about pictures like this, which will be fun. We end the term with something that's totally separate that the engineering, physics, sciences want you to know, which is Taylor series. Super interesting. I have a lot of stuff to say about it, but it's this idea of approximating a function like this with ever increasing accuracy using polynomials. I'm going to send this going, and it's super cool. So anyways, there we go. You can see how it approximates. That's the error, that little bar. We'll talk about that. And there it approximates. And we'll do the same thing for other functions. For example, e to the x. This is e to the x. We're going to approximate it. And I got a lot I can say about that. All of these things I'll explore in a little more detail, and I'll give you the opportunity to ask me follow-up questions. So I'm excited about teaching it. I hope you sign up. I hope that information helps you decide whether it's the right course for you.